Hello everyone, welcome to the fourth lecture of this first module. The first module we are discussing about fundamental of measurement system, and this is the course on measurement and instrumentation. In the previous class we started our discussion on noise, and the noise in the output of an instrument is broadly classified into three different types. They are generated noise, conducted noise and radiated noise. What we are going to do is we are going to discuss each of the noise in little detail, okay, so that we understand the sources of noise, which is very important when at least you are the end user, okay. Let us try to understand this generated noise with the example of an amplifier. Consider this amplifier and you have a say input voltage Vi, which is the say input signal that you are giving to this amplifier, and this is without any noise, okay. Say the gain of the amplifier is say AV, which is say AV is the, or if you have this output voltage is AV into say Vi, right. We are discussing this amplifier because amplifier, you know, that is a part of measurement system. This is a very important part of a signal conditioning circuit of a measurement system, okay. So this is your output voltage. Usually, ideally you should get this voltage, but what we usually get is the output signal plus another component, which is the noise component, okay. Now there is no other source of noise in this configuration than from where this noise is arising. That is the important question, okay. So what happen is the power supply in this case is actually serving as a source of energy, because you know that for every amplifier you call it say based on FETs or say BJTs, you are providing certain biasing, right. So either you are giving say VCC or VDD to this all this amplifier based on this transistors, okay. So basically the power supply basically is the source of energy for the operation of this amplifier, right. The output signal, as I have mentioned, is the gain times the input signal plus some other voltage, which is basically the noise voltage, okay. Now, what is the source of this noise? Because you are doing this experiment in say very stringent conditions, so there should not be any external noise, okay. So from where this noise is coming, okay. So one of the possible source of noise is on account of internal component of the amplifier. Like you know that all these amplifiers are built up using some active component as well as some passive component, like say resistors, capacitors, etc., okay. So all this active and passive component may generate some noise, okay. So noise generated by this is inside the amplifier, okay, and therefore this noise is known as the generated noise, okay. So the internally generated noise is on account of the components that I have just mentioned, be it active component like transistors, diodes, etc., or the passive components like resistors, capacitors, inductors, okay. Let us try to understand another important component of this noise, which is the Johnson's noise, okay. This is also known as Johnson-Nyquist noise. We will see that what it is, okay. Let us try to understand the Johnson's noise, okay. To understand the Johnson's noise, we have to understand the operation of a simple resistor, okay. So if I talk about a simple resistor, the conductive portion of a resistor consists of a regularly arranged group of atoms that maintain the same general physical position in the conductor, okay. So many of the atoms are at equilibrium, most of the atoms are at equilibrium when you do not agitate it by any means, okay. Now they are in a state of rapid vibratory motion because of the temperature or certain thermal effects. Even you talk about a room temperature, still you have around 300 Kelvin present. Okay. So, they are in a state of rapid vibratory motions. Okay. Now, this vibratory motion of atom is transferred to the conduction electrons, thereby producing a noise component of a current. Okay. Now, since this noise is a temperature dependent, it increases with internal heating. Okay. So, this temperature dependent noise is known as the Johnson's noise. Okay. So, you can understand this as a thermal noise also. Okay. So, in fact, the Johnson's noise, as I have mentioned, is also known as Johnson-Nyquist noise, as well as this is also known as thermal noise, or sometime it is also called Nyquist noise. Okay. So, all are same, and this is because of the history of the generation of this noise, okay, or the prediction of this noise. Okay. So, it was basically first measured by Johnson at Bell's lab, okay, and then he described this whatever he has measured to Nyquist, who was also at the Bell lab, okay, and then Nyquist was able to explain the cause of this noise, and that is why the noise is known as Johnson-Nyquist noise. Okay. The noise level can be calculated in the terms of voltage by using a constant known as Boltzmann constant, which you are already aware of. Okay. So, the equation for the thermal noise is given something like this. This V is the noise voltage, and this can be given as 2 into root KTRB, where this V, as I have mentioned, is the thermal voltage or the open circuit Johnson noise, of course, in terms of voltage, and K in this case is the Boltzmann constant. Okay. Now, T is the temperature measured as degree Kelvin in this equation, which you know that is the degree Celsius temperature plus 273.16. Okay. R is the value of the resistance provided by the resistor. Okay. And the unit, of course, is ohm, and B, this B is the range of frequency being applied, or basically the bandwidth. Okay. And the unit of this is, of course, hertz. Okay. So, this is the basic thermal noise or the Johnson noise. Okay. This can be, of course, explained by various means, and one of the explanation is something like this. The noise power you have to understand to get this equation. Okay. So, in brief, if I say the noise power generated in a conductor can be written as kT into del F, okay, where this K is the Boltzmann constant, which is given by 1.38 into 10 power minus 23 joule per Kelvin, okay, and this T is the absolute temperature of the resistor, and this del F is the bandwidth of the noise signal. So, this is the noise power generated in a simple conductor, or you can say the resistor. Okay. The noise generation system can be represented by simply a voltage source, say of magnitude this En, in a series with the equivalent resistance Rn. Okay. So, this is the representation for the noise generating system. Okay. Noise generating system can be, say, represented by a voltage source En in series with a resistance Rn. Okay. Now, if the noise generator is connected to an external load, say RL, okay, the noise energy will be transferred to the load. Okay. Now, let us recall the maximum power transfer theorem. Under the condition of the maximum power transfer theorem, the RL and Rn, when they are equal, the maximum noise power will be delivered to the load. Okay. Now, in this case, if you calculate the power, it is given as En square by 4 Rn, or if you calculate the potential, it is En square given as 4 R PNL, and the power we have just seen from this equation. Okay. So, if I put this value in that particular equation, what we will get is 4Rn into Kt into del f, and that's how the noise voltage is calculated as 2 under root Kt Rn into B or del f, which is the bandwidth. And exactly this value you have seen for a thermal noise. Okay. Now, if you see the vibrations produced by the thermal effect within a resistor covers a really large frequency range, okay, and therefore, the noise generated consists of a wide spectrum of frequencies. Okay. So, this wideband noise is also known as the white noise. Okay. This please note that in signal processing, white noise is a random signal having equal intensity at different frequencies, giving it a constant power spectral density. Okay. And the power spectral density, you know, that is defined as the noise power per unit of frequency bandwidth. Okay. So, the concept of white noise, I think, should be clear. This is known as white noise because you are having a wide spectrum of frequency for the generated noise. Okay. The power spectral density represents the noise energy generated per cycle of vibratory motion in the generated conductor and can be given as something like this. Okay. So, the power spectral density, as the name suggests, is can be calculated by this Pn by del f, and again if you recall the formula for this power, okay, this Pn was Kt into del f, okay, and that is how you get the power spectral density as Kt. Okay. So, as I have mentioned, the thermal noise in an ideal resistor is approximately white in nature. Okay. Means that the power spectral density is nearly constant throughout the frequency spectrum for the resistor. Okay. But it does decays to 0 when you talk about very high frequencies. Okay. So, when limited to a finite bandwidth, the thermal noise has a nearly Gaussian nature. Okay. So, another important noise, particularly if you talk about instrumentation which is based on semiconductor devices, is the short noise. Okay. The internally generated noise in a semiconducting device on account of the random movement of the charges is called the short noise. Okay. Not much can be done to reduce the internally generated noise in the semiconductor device, as this noise is on account of acceleration of charges. Okay. So, what could be the solution? The selective filtering can be helpful to some extent in reduction of this noise, but still this short noise persists. Okay. So, you cannot make it 0. Okay. So, this noise will persist, but then you can minimize this. Okay. Then I hope that the generated noise is clear to you, and then after that we have a conducted noise. Okay. Now, this conducted noise is not because of the internally generated noises. Okay. So, let us try to understand that what is the cause behind this conducted noise. Okay. The power supply of the amplifier could be the source of this conducted noise. Okay. Because the power that you are supplying to the amplifier, say the biasing I am talking about, okay, because it may not be say a pure DC. Okay. It may have spikes, it may have ripples, or some random deviations can happen. Okay. So, that are conducted to the amplifier circuit, say through the power wiring. Okay. This type of noise is called the conducted noise. Okay. So, if you see this has not been generated in the amplifier, but the external source through which you have connected, it is conducting that. Okay. Then another kind of noise that we have seen is the radiated noise. Okay. So, there may be electric or magnetic field or disturbances in the ambient around the amplifier, because of which unwanted signal are radiated into the interior of the amplifier, and this is known as radiated noise. Okay. So, three different types of noise I think we have seen: generated, conducted and the radiated noise. Okay. So, once we have the basic understanding of the noise, we should also learn about different errors in the measurement that can occur. Okay. Because errors we have to deal with regularly in our laboratory or even in the real world. Okay. So, the manufacturer of any instrument has to basically specify the deviations from the nominal value of a particular quantity which is being measured. Okay. The limits of this deviation from the specified value is known as the limiting errors. Okay. This limiting error is also known as the guarantee error. We will see why this is also known as a guarantee error. Okay. So, let us try to understand this limiting error and then we will move ahead. Okay. Say the magnitude of a quantity having a nominal value A, for example, and a maximum error or limiting error of plus minus delta A must have a value which is between A S minus delta A and AS plus delta A. Okay. So, this value must be in between certain limit, okay, or in certain range. Okay. So, let us try to understand this with the example of a resistor. Okay. So, the nominal magnitude of a resistor is say 100 ohm, okay, and the limiting error is plus minus 10 ohm. Okay. So, the magnitude of the resistance will be this 100. Okay. So, 100 ohm plus minus 10 ohm. Okay, means the value should be in between 90 to 110. All right. So, this limiting error is very important for the operation of any instrument, because you should operate this in the range where you are sure that your manufacturer has provided you the limiting errors. Okay. So, this is also known, as I have mentioned, as guarantee error, because the manufacturer basically guarantees you that the value of resistance of the resistor that you are going to use is between 90 ohm to 110 ohm. Similarly, in this case, the magnitude of the quantity which is having a nominal value AS is guaranteeing you that this value will be in between AS minus delta A to AS plus delta A. Okay. So, there is another concept of limiting error, which is the relative limiting error. So, the relative or the fractional error is defined as the ratio of the error to the specified or the nominal magnitude of the quantity. So, relative error is given as the actual value minus the nominal value divided by the nominal value. Okay. So, relative limiting error can be calculated like the error value divided by the expected value or the nominal value. Okay. So, this is the basic concept of limiting and relative limiting errors. Okay. Now, let us see that when you combine two different quantities, okay, how this limiting error will behave. Okay. Now, let us try to understand this with the example of two different quantities x1 and x2. Okay, and say x is the function which is the say summation of these two quantity. Okay. Now, x is given as x1 plus x2. Okay. Now, the relative increment of the function can be given as dx by x equal to d x1 plus x2 by x or dx1 by x plus dx2 by x. Okay. Now, expressing the result in terms of the relative increment of the component quantities, we can have what we are going to do is, let us multiply both the terms with x1 by x1 and x2 by x2. Okay. So, dx by x is given as dx1 by x into x1 by x1 plus dx2 by x into say x2 by x2, because they cancelled out, right. So, we are actually multiplying it with 1. Okay. So, when you multiply this with x1 by x1 numerator and denominator. Similarly, x2 to the second term. Okay. After rearranging, what we get is dx by x equal to x1 by x into dx1 by x1 plus x2 by x into dx2 by x2, right? Now, if the limiting errors in the component quantities are represented by plus minus del x1 and plus minus del x2, then the corresponding relative limiting error in x can be given as del x by x as plus minus x1 by x into del x1 by x1 plus x2 by x into del x2 by x2. Okay. Now, the below equation that you have just seen shows that the resultant limiting relative error is equal to the sum of the products formed by multiplying the individual relative limiting errors, which is del x1 by x1 and del x2 by x2, okay, by the ratio of each terms to the function. Okay. So, del x by x is given as plus minus x1 by x into the individual relative limiting error in say x1, say I am calling this term as say a1, okay, into a1 plus x2 by x into a2. Now, if you have summation of more quantities, this will be continue, like del x by x is equal to plus minus x1 by x into a1 plus x2 by x into a2 and so on, where this a1 and a2 and all are the individual relative limiting errors in those individual components. Okay. So, this is very important conclusion. Okay. Now, this is about the sum of two quantities. What if we have difference of two quantities? Okay. Now, if we have say difference of two quantities and say x is equal to x1 minus x2, okay. Now, let us express the result in terms of the relative increment of component quantities. We have this del x by x as dx1 by x minus dx2 by x. Again, if I multiply like we have done in the case of summation, okay, with x1 and by x1 and x2 by x2, and again rearranging this, we get this equation where dx by x is equal to x1 by x into say dx1 by x1 minus x2 by x into dx2 by x2, right. So, this is what we get. Okay. Now, if the errors in x1 and x2 are plus minus del x1 and plus minus del x2 respectively, the sign may be interpreted to give worst possible discrepancy. Okay. So, when the error in x1 is plus del x1, the error in x2 is minus del x2, or say in vice versa, error in x1 is minus del x1 and x2 is plus del x2, then the relative limiting error x can be given as del x by x equal to plus minus x1 by x into del x1 by x1 plus x2 by x into del x2 by x2. Okay. So, this is the same form that we have seen for the summation, or the final conclusion that we have seen during the summation of two quantities, which was the resultant limiting error is equal to sum of the products formed by multiplying the individual relative limiting error with the ratio of x1 to the function. Okay. Same we are getting when you have difference of two quantities, of course considering the worst possible discrepancy. Okay. Now, you can have multiple conditions where x1 and x2 are much larger than x or much smaller than x. You can have special conditions for all these cases. Okay. So, this is about sum and difference of two different quantities. Now, let us try to understand this, what will happen to a function which is a multiplication of two different components x1 and x2. Okay. So, if I take log both side, I have a log x equal to log x1 plus log x2. Okay. Now, if I differentiate this equation, okay, I can have 1 by x equal to 1 by x1 into dx1 by dx plus 1 by x2 into dx2 by dx. Now, if I rearrange it, I have dx by x equal to dx1 by x1 plus dx2 by x. Okay. So, now if I represent the error in x1 and x2 as plus minus del x1 and plus minus del x2 respectively, the relative limiting error in x can be given as del x by x equal to plus minus del x1 by x1 plus del x2 by x2. Okay. So, if you see this, what we can conclude is the error in this case is the summation of the errors, or the relative limiting error in the function is the summation of relative limiting error x1 and relative limiting error in x2. Okay. Or similarly, you can have multiple components, okay, x3, x4 like that. Okay. What is different from the summation or the difference is, in that case you had multiplication with another factor which is missing over here. Okay. Now, let us see for the division or quotient of two different quantities. So, x is in this case is written as x1 by x2. Okay. Again, if you take the logarithm and differentiate it and rearrange the equation, you will get the value as dx by x equal to dx1 by x1 minus dx2 by x2. Okay. Now, if you rearrange or if you represent the limiting error in x1 and x2 as plus minus del x1 and plus minus del x2, and consider the worst case when del x1 by x1 is positive and the other term which is del x2 by x2 is negative, or say vice versa, means the del x1 by x1 is negative and the del x2 by x2 is positive. Okay. The relative limiting error in x can be given as del x by x is equal to plus minus del x1 by x1 plus del x2 by x2. Okay. So, if you see the relative limiting error in x is the summation of relative limiting error in x1 and plus the relative limiting error in x2. Okay. And this takes the same form as we have seen for the product of two quantities. Okay. You can have multiple structure like this, say if you have say power of a factor. Okay. So, x is given as x1 to the power n. Okay. In this case, what will happen to the relative limiting error? Okay. So, if you take the log, okay, and then differentiate, what you will find is the relative limiting error in x is equal to the power times the relative limiting error in x1. Okay. So, if you have say this del x1 is plus minus del x1, okay, the relative limiting error is given as plus minus n into del x1 by x1. So, it is clear that the relative limiting error in the result under these circumstances is magnified actually by n times. Okay. So, it is the n times the individual component of relative limiting error in x1. Okay. So, this is a little bit on relative limiting error, which is a very important factor for a very important factor for a instrument. Okay. There can be different type of errors. Okay. Error can arise from different sources and in the instrument and can be classified as a gross error or a systematic error, or it can be random in nature. So, you have three different kinds of errors, which are gross error, a systematic error and a random error. Okay. So, in our final lecture on in this module 1, which is the 5th lecture, okay, we will talk about these different type of errors, and we will also try to see some of the dynamic characteristics of a instrument. Okay. Thank you.